Welcome to EGR445 and 598. In today's class, we are going to talk about some important design elements. In today's class, first, I want to talk about design of shafts. Design of shafts. And after design of shafts, I want to talk about design of keys and coupling. So keys and coupling are needed to connect two or more shafts. Then at the end, I would like to talk about design of springs. And we will have a couple of breaks.
Will you be touching base on the turnbuckle?
Okay, you want me to cover turnbuckle? All right, design of turnbuckle as well. Okay, so we will try to cover these topics, and if you have any questions, you're welcome to stop me and ask. If the students that are online, if they have any questions, you are welcome to unmute yourself and then ask me questions. So first and foremost, what is the difference between the rod and a shaft? So rod versus shaft. Now, when you looked at the cotter joint and knuckle joint, we designed rods. So rods are for force transmission and shafts are for torque transmission. And again, rod can transmit power, but the power equation is power is equal to force times velocity. Shafts can also transmit power, but the equation is power is equal to torque times angular velocity. In the last class, we looked at the equation for shear. So shear stress equation is used for power transmission design of shafts. So you can have this equation, T divided by J is equal to tau divided by R. This is the fundamental equation of torsion that relates how torque is related with the polar moment of inertia and the shear stress that is induced in the shaft. So T stands for torque, J is polar moment of inertia, tau is the shear stress, and R is the radius. Now, one thing I want you to understand, probably you have seen the exact same equation when you studied mechanics of material or engineering design. But the difference here is this J and this is R. They pertain to the dimensions of the shaft. Torque comes from the power transmission requirement. This is a requirement. and tau is the material property. Now, what it means is the torque value would be given to us. Either it would be given to us directly or indirectly. What does it mean? So sometimes they would specify power is equal to 2 pi nt divided by 60, where P is the power in watts, N is the speed in RPM, and T is the torque in Newton meter. So if power is given to us, RPM is given to us, we can find out the value of torque. From this equation, value of torque can be known. Second thing is, sometimes they will specify the material, whether the shaft is made up with mild steel, shaft is made up with alloy steel, or shaft is made up with some special purpose material. So tau value will be given to us. So based on value of T and value of tau, we have to find out value of J or R. So that means we have to find out the dimensions of the shaft. And that's all we are going to do. Now, if you have a simple shaft design, what do I mean by simple shaft design? When I say a simple shaft, means if you have a shaft and one end of the shaft is connected to, say, an electric motor, and other end of the shaft is connected to, say, a generator. So you have a motor and maybe a generator here. And for the analysis purposes, we assume the shaft to be massless. So think about, this is the shaft. And so mass is very small. Mass is very small. So in this particular case, you can use the equation that we have shown over here. So this equation, I'm going to call this equation 1. Equation 1 can be directly used because this shaft is subjected to pure torsion. There is no additional loading except torsion. So you can just use the equation for torsion and get done with it. And this is probably what you did in mechanics of material, EGR445 or EGR444. However, the case becomes complicated when, in addition to the torque, there are some forces. And please understand, pure torsion case is never possible in actual practice because shafts cannot be massless. Shafts will have mass, which means shafts are going to have their self weight. So if you want to assume the distributed mass, then the shaft is going to have its own self weight at the CG of the shaft. So what that means, if you were to draw the free body diagram, what you have is you have a load at the center span. So this is the weight of the shaft, which is W, that is at the center span. And what would this load do? This load would deflect the shaft and give rise to bending moment. So if you were to draw the shear force diagram, you're going to have a shear force diagram something like this, and you're going to have a bending moment diagram something like this. This is called as shear force diagram. This is called as the bending moment diagram. But realize now the problem all of a sudden has become complex, because I have a case. I want to design this shaft, but on this shaft, I have torsion and bending. Do you agree with me? So, which means bending stresses and torsional stresses coexist. And what happens when you have simultaneous action of normal stress and shear stress? What happens? Remember in last class we talked about it. You have the normal stress and you have the shear stress, and both of them are acting simultaneously. That give rise to principal stresses and maximum shear stress. Everyone understood this? So since in this particular case, on this shaft, you have normal load, normal stresses plus shear stresses, both of these will give rise to principal stresses. I'm going to call this sigma P and tau max. Now, in EGR444, you must have studied something called as the failure theories. Now, what is the practical interpretation of these failure theories? Now, please try to understand. Engineers and scientists observe a physical phenomenon, or they observe an experiment, and then they try to formulate what could be the logic behind that particular behavior, behind that particular phenomenon. So for an example, if you have a shaft and you observe that that shaft is failing. So if the shaft is failing, the predominant mechanism with which the shaft is going to fail is shear. Now, what is the theory that can actually explain that shear failure of the shaft? And the theory that can describe the failure of shaft is maximum shear stress theory. And that's why when we design the shafts, we use maximum shear stress theory to kind of design the shafts. Let me take a step back, and I want to give you one more simple example. There is also something called as the maximum principal stress theory. Have you studied theories of failure in EGR 444? Did anyone take EGR 444?
Yes.
Okay.
I took the EGR445, which is the mechanical design.
Yep. So did you study theories of failure?
Yeah.
Okay. So what about you? Did you study theories of failure? So the way so basically, let me give you a simple background on what do we mean by theories of failure. So engineers and scientists perform the experiments, and they observed that for certain loading conditions, the material fails in a certain fashion. As an example, if you have an aluminum rod, and if you place that aluminum rod in a tensile testing machine and pull two ends slowly, the aluminum rod is going to fail at 45 degrees. Aluminum under slow loading would always fail at 45 degrees. And the reason for that is, if you look at the material properties and the grain structure, material doesn't care about theories of failure. Material is going to fail wherever it's weak. So what that means is aluminum is weakest at 45-degree plane. And that is the plane which is the weakest plane. So when we design the aluminum, we have to design the aluminum parts so that it is safe at that orientation. So all these theories of failure, they try to justify or come up with some type of logical argument on the the failures that are observed in engineering. One thing I want you to understand that these failure theories are all good and valid when the loading is slow. The theories of failure, they change when the loading is quick, which means if you have high strain rate or dynamic loading, the failure theories that you studied will no longer be valid. And there are additional considerations that you need to take into account when you study the failure under dynamic loading. But as far as the basic component design is concerned, we would assume that loading is static or quasi-static and design the components. As we go towards the internal combustion engine design or design when the loading is dynamic, we will talk about how do we account for the loading when the loading is changing with respect to time, and how can we correct our design assumptions. So with that, all that said, here is the design procedure for shafts. So design of shafts. Step 1, find torque. And this torque is P is equal to 2 pi nt divided by 60. From this equation, find out what is the value of T. Now, one thing I want you to understand, this T is steady state torque, which means this is the torque that is transmitted continuously. Say for an example, when the generator is in motion or when the internal combustion engine is in motion, but the starting torque is typically higher than the steady state torque. So the design that we do, for example, if we design a generator, if we design an internal combustion engine, or even if we design the shaft, we want that design to be safe, not only at steady state conditions, but also at the starting and stopping conditions. So what we do is we kind of modify this torque value T based on the operating conditions. A simple example is if you have an engine that runs 8 hours a day, that is considered to be normal duty. If you have an engine that runs 24/7, that means that engine is heavy duty, and the design considerations are different. Factor of safety are different. The service factors are different. Now, I don't know if you have seen this. Imagine you go to buy a treadmill. Treadmill that is for home use is different than the treadmill that they put for gym or commercial use. And the treadmills that are designed to take abuse in the gym or in a student union or some other activity center where basically anyone can go and use it again and again and again and again. So those are designed with higher factor of safety, better materials, and they are more rigid because the duty factor is significantly higher. Now, one interesting exception to this is automotive cars. For an example, if you think about the rental cars are typically abused, but the automotive manufacturing and design has evolved so much that the cars that they are provided to the regular customers, the same cars are provided to the rental car agencies. But I want you to understand, if you think about that mechanical system, which is an automobile, that has about 7,000 to 8,000 parts. And still those cars run for 150, 200,000 miles. So that's an engineering marvel. So that's why if you look at the internal combustion engine design, for that whole thing to work and be efficient at the same time, all these pieces need to work in sync. So that, in my personal opinion, is a mechanical engineering excellence. The only difference is, suppose if we are building cars for military use, where they will be significantly abused, they will work in the high temperature, high humidity, or corrosive environments, then your design principles would be different. And again, you have to balance the requirements, because for military use, you want a robust, a reliable vehicle that can survive and perform in an operation theater or hostile territory. But for consumer use, you want a vehicle that is comfortable, that can reliably take from point A to point B. It's usually not used for off-road conditions, but it needs to give good fuel economy. So the designer, there sometimes could be conflicting requirements that you have to manage to come up with a final design. So based on the duty factor, typically you would modify T design is equal to 1.1 to 1.2 times torque. Then step number 3, find loads on shaft. So you would see what's happening. A simple example is, if you have a shaft, and on this shaft, you have one gear here and maybe one pulley here. You have one gear here, you have one pulley here. And this shaft is like simply supported at these two ends. So the loading is, this is the weight of the gear, WG, and then there will be weight of the pulley, which is WP. So what you want to do is, you want to draw the free body diagram. Everyone comfortable in finding reactions at the supports? So you can find out the reactions at A and B. You can find the reactions at A and B. And the reactions can be found out with the equation summation of forces in the y direction is equal to 0, summation of moments is equal to 0. And then you can draw the shear force and bending moment diagram. Here, the shear force diagram most likely is going to look like this. And once you are done with the shear force diagram, you will draw the bending moment diagram. And this bending moment diagram, say, most likely would look like this. So this is point C, this is point D. This is point A, this is point B. As you can see, the bending moment, this is shear force diagram. This is the bending moment diagram. The shear force at A and bending moment at A is given to you. You would select the maximum bending moment. And in this case, this is the maximum bending moment, BM max. So find loads on the shaft. Find maximum bending moment. And then please understand, when we are designing the shafts, we have to use maximum shear stress criteria. So to find maximum shear stress criteria, I will write this down. Max shear stress criteria. So for maximum shear stress criteria, you would find out value of T max, which is square root of Bm max square plus T square. And some of you may ask me, what is the logic for this? I don't know. Have you looked at shaft design for composite loading in your design course? Did anyone look at it?
So 3 years ago or 4 years ago.
So this is a shortcut, and remember this works. So typically or conventionally, the composite loading shaft design is taught like this. What you do is you find out the bending moment. From the bending moment, find out the maximum bending stress. From torque, find out the maximum shear stress. Plug those numbers in to find out the tau or the T max and equate that T max to the design shear stress. So that is the procedure. What is the problem with that procedure? At the end, you get a very, very complicated equation that needs to be solved by trial and error. If you have not done it, I encourage you to try solving in that approach. So, and you should actually work out to appreciate how simple this approach is. So idea is the same. You have the bending stress and you have the shear stress. Bending stress and shear stress, they are perpendicular to each other. So what you do is you find out the equivalent stress, which is basically the maximum shear stress. And equate that maximum shear stress to the design stress. But here, what we are doing is something different. We are saying bending moment is perpendicular to twisting moment. Bending moment is perpendicular to twisting moment. So I'm trying to find out a resultant twisting moment that is because of the bending moment and the twisting moment. And I would find out the torsional stresses based on this resultant twisting moment and equate that to design stress. So tau design is equal to T max divided by J multiplied by R. And depending upon whether the shaft is solid or whether the shaft is hollow, you can use the equations for J as pi d raised to 4 by 32, or J is equal to pi by 32 d outside to the 4 minus d inside to the 4. And R is always d outside divided by 2. Everybody understood this? This number, this tau design, either will be given to you or you can use design data to find out this value. T max comes from equation step number 5, and at the end you get the dimension of the shaft. Everyone understood this procedure? Any questions? Now I'm going to work out some problems, but before I actually work out the problems, I want to talk about keys and coupling, actually keys, and then I will work out a complete problem. Students online, any questions? Okay. Now the next question is, say we have shafts, say we have multiple shafts, and we want to attach those together. A classic example is, say for an example, you have a motor, electric motor. This electric motor needs to be connected to a pump. This electric motor needs to be connected to pump. And there is this impeller and there is this pump. So how do we connect these two shafts? So for that, what we do is, say we actually, depending upon how far they are, we actually add another shaft in between, and then we add couplings. One coupling here, one coupling here. And depending upon the power requirement that we are looking at, you could have a simple muff coupling. So what is a simple muff coupling? In a simple muff coupling, you have one shaft end. On this shaft, there is a keyway. Then there actually you have a sleeve. You have a sleeve. And then you have this second shaft. And again, to connect these together, what you have is, you have keyways on both sides. And what you do is, you add keys here. So key is like a rectangular piece of bar. So something like this. So we have this coupling. So this is shaft 1. This is shaft 2. And we have key here. And key here. So how does the power get transmitted? So what you have is, you have an input shaft here. So input, and you have an output shaft over here. Input shaft is attached to this muff, also called as the sleeve coupling. So input shaft is attached to the sleeve by means of a keyway. So if you look at in the front view, this muff would be something like this. There will be shaft, and this will actually be sort of fitted inside. And then here there is going to be key. So this is the key. So the input shaft will rotate the muff. That muff will rotate the key that is locked onto the second shaft, and then that key would start rotating, and that key would rotate shaft number 2. So if you think about the power transmission, it's going to be from the shaft to the key, key to the muff, muff to the second key to the shaft. So that is how the power transmission is gonna happen. Now, one thing I want you to understand, keys are like mechanical fuses. So for an example, in this power transmission assembly, or in this mechanical system that comprises of shaft 1, key 1, muff, key 2, and shaft, which is the cheapest and the easiest thing to replace? So the obvious answer is the shaft number 1 is attached to the motor. Shaft number 2 is attached to pump. If either of those shafts break, then we have to overhaul or we have to refurbish the motor or the pump. So the easiest way we can fix this assembly is replacing a key. So key is designed to fail in the case of overload. And that is something called as the fail-safe design. Because think about this. We have this pump, and this pump is designed to pump water. And all of a sudden, the water is contaminated. And then maybe there is mud. Because of that mud, the pump gets stuck. If the pump gets stuck, motor is still going to try to rotate, and essentially it will draw more current to the point that motor armature would burn. So if we design in such a way that if the torque requirement exceeds certain threshold, that key would just snap. It's sort of a mechanical fuse. There are multiple levels of redundancy and multiple levels of fail-safe in a system like this. It can also have an electrical fuse, which means we are sure that if something goes wrong in this system, the pump should not break, the motor should not break, but you have a breaker that turns off, or you just have a key that gets sheared off. So if you want to start or fix that assembly, you just just see where the problem is, fix the problem, turn the breaker on or replace the key, and the system starts working again. So the next question is, how do we design this key? What type of failures are possible in the key? There are many types of keys. There is a rectangular key. There is a square key. There is something called as the Woodruff key. There is a key with maybe a set screw just to make sure that it is located properly. But the design principles behind the keys is the same. And I'm going to try to explain that with the example of either a rectangular key or a square key. So let's understand. Yeah.
Which kind of key is the most popular one?
It completely depends upon design.
Oh,
So just to give you an example, I have seen, and once you work in industry, you will see keys like this. So you will see keys that are square. You will see keys that are rectangular. You will see keys wherein they have some sort of a stub on one side. So you will have keys like this. you see keys where what you have is the problem with keys is you don't want them to vibrate and come undone. So for that, sometimes what you have is you have some type of a set screw that actually holds the key in place in operation. So there are many designs, but please try to understand the keys and couplings are used because we cannot weld these shafts together. So for an example, say if I have a motor shaft and if I have a pump shaft, I cannot weld them together. That's not going to work because first and foremost, welding would cause enormous amount of thermal stress. It will break the seals. It will start leaking. It will reduce the life of the component. And also it will not maintain the circularity and concentricity that are required for proper operation. So which means if you have an offset, then you realize that it's actually going to make the whole thing wobble and affect the performance negatively rather than a smooth and continuous transmission. Now, one thing observed in muff coupling is nothing but a hollow shaft. So if you look at the muff, how does this muff look like? Muff is nothing but a sleeve with a keyway. So muff is nothing but a sleeve with a keyway. What are the disadvantages of muff coupling? Muff or sleeve coupling cannot be used for large power transmission. But a very simple example is, how many of you have seen the 3D printers? 3D printers, have you seen that the 3D printers are the XYZ rails are controlled by stepper motors? And if you have seen the coupling that attaches the stepper motor to the lead screw is like a sleeve coupling. But what is the difference in the sleeve coupling that is used for in 3D printers? This sleeve would have slots. This sleeve would have slots. And since the power transmission is small, rather than using a key, what they do is they just use a set screw. And what does the set screw do? So if you look at the stepper motor shaft is a D shaft. What do we mean by D shaft? So stepper motor shaft, if you see, basically it's like this. It's a D shaft. And this set screw goes and fits into that D. So think about it, that set screw is acting like a key. But since the power transmission requirement is so small, you don't need the whole key. You just need a very teeny tiny piece that will keep that muff coupling or that coupling and the stepper motor shaft together. Now, what is the purpose of these cuts? So let me explain you the biggest disadvantage of muff coupling that will make everything clear. This muff coupling is a solid and rigid coupling, which is good, but that means that it will not tolerate slight misalignment between the shafts. And that can happen because of the tolerances, because of wear and tear, because of the temperature, because of the humidity, because of the corrosion, that these two shafts, ideally supposed to be concentric, will no longer be concentric. They will be slightly offsetted, or the bearings, they worn out, and that will give you some tolerances, and these shafts could have a linear misalignment or could have an angular misalignment. Muff coupling cannot tolerate any type of misalignment. And what that means is power transmission will no longer be smooth. As a matter of fact, if you use the muff coupling on the shafts that are misaligned, that would increase the stress on the bearing and would lead to premature failure. Now, what happens in the case of a coupling with these slots? It adds compliance. What that means is, even though it's a muff coupling, by removing the material, you are allowing that coupling to deform slightly. I mean, when I say slightly, I have to be very careful. You can't tolerate 5 degrees of misalignment or 10 degrees of misalignment or 30 degrees of misalignment. You need to use a universal joint, or you have to use a gear if you have that much amount of misalignment. But maybe half a degree to 1 degree misalignment, or half a millimeter to 1 millimeter misalignment, this compliance in the coupling would account for that misalignment. The second thing is, as soon as you start, you have these cuts, essentially what happens is, it's like you are adding a spring between these two. So as soon as, if you have a coupling like that, then you add springs. What is the advantage of springs? The spring would minimize the shocks. It absorbs the teeny tiny amount of shocks. And in the case of 3D printers, as you know, the stepper motor starts, stops, starts, stops, starts, stops. So basically, the teeny tiny vibrations from the stepper motor, they do not get transmitted to the lead screw, because that would affect the quality of the parts. So this coupling, this is an inexpensive way to compensate for misalignment and to compensate for shocks, vibrations, and jerks. But be careful, this is only applicable for small power transmission. For large power transmission, you cannot use this, and you need to have some type of a rubber or elastic element between the input and the output shaft that will absorb the shock, or that will actually take care of the misalignment. Everyone understood this? Online students, any questions? So the next point of discussion is, if this key has to fail, how would this key fail? And it's very simple and easy to see. So think about it like failures of key. So this key can fail in crushing. And what do I mean by that? Is I want you to kind of observe that this is the shaft. And there is this key. So if you look at this key over here, half of the key is inside the shaft, half of the key is inside the coupling. So you have this key, half of the key is inside the shaft, and other half of the key is inside the coupling. So this shaft will bite into key, which means shaft can crush the key. What is the area that is resisting? So if this dimension is height, and if this dimension is length, crushing area is half of the height multiplied by length. Do you agree with me? That is the crushing area. The next question is, what would be the force on this area? And the force on this area is force is equal to torque divided by the radius of shaft. So for the crushing failure, sigma c is equal to F divided by 1/2 times H times L. Everyone understood this? This is the crushing failure of key. So what other type of failure is possible? Can someone tell me what can happen? How would key fail?
Shear.
Key could be sheared. What do I mean by key sheared? Which means half of the key would remain in the shaft, a remaining half, the top half of the key, would remain in coupling, and basically coupling and the shaft would separate. Everyone understood this? It's like, think about slicing the key across. So the next type of failure of the key, and I'm going to show you the top view of the key. Is shearing. This is L and this is W. Are you with me so far? This is the shearing. So tau is equal to F divided by W times L. Are you with me so far? Any question, concerns, ideas, doubts, thoughts? So, believe it or not, we have covered significant amount of material in a very short period of time. So what I'm going to do is, I'm going to give you a step-by-step recipe to design a muff coupling. Are you with me so far? Okay. So design of sleeve, also called as muff coupling. First few steps from shaft design are as is. So you are going to have 1, 2, 3, 4, 5, and 6. When you are asked to design any coupling, step 1, the first part is design of shafts. Everyone understood this? So you would follow these 6 steps to design the shafts. So step 1, 2, 3, 4, 5, 6. Next step is design of key. And at this point, you have to kind of decide whether you want to design a rectangular key or you want to design a square key. So what does it mean? If you have a rectangular key, if you have a rectangular key, typically this dimension is d by 4 by d by 4. So you have a rectangular key which is d by 4 by d by 4. Sometimes I have seen people using the rectangular keys with d by 6 and d by 6. So you can use d by 6, d by 6. So you can choose a square key or you can use a rectangular key which is d by 4 and this is d by 6. Are you with me so far? So essentially, once the shaft is designed, the primary dimensions for the key are known. So which means cross section is known. The only parameter that is unknown at this point is the length of the key. Are you with me so far? Now what I want to do is, just to remind ourselves, I want to write down these two equations for key side by side. F divided by 1/2 H L is equal to sigma C, and tau is equal to F divided by L multiplied by W. So before I actually discuss, I want you to understand the process here. H and W are decided by the dimension of the shaft. Are you with me so far? The only problem is what should be the value of L. And at this point, we have two equations. So here is what you can do. You can find out the value of L from this sigma of C is equal to F divided by 1/2 H. Find the value of L. Do you agree with me? And then check if for this computed value of L, if tau is less than the design shear stress for the key. Everyone understood this? Otherwise, what you can do is, here another way of doing it. You find out L from sigma C, you find out L from tau and take the largest value. Everybody understood this? That saves the same purpose. At the end of the day, what do we want? We want our design to be safe. And what we do is, to check if the design is safe, we find out the value of L from sigma C equation and check for tau equation, or we actually find out the two values of L and select the largest value. Are you with me so far? Any questions from online students? But there is something else I want to talk to you about. How many of you know about the stress concentration? Stress concentration? Yeah, you should have studied that. Trying to remember.
On my stresses.
So let me give you an example. Imagine you are driving on 202 West. Okay, so you are driving. So this is 202 West. Okay, and these are the lanes, and you get vehicles going, vehicles going, vehicles going, vehicle going, vehicle going, vehicle going, and all of a sudden there's an accident in the center of the road. So what happens? These vehicle lanes kind of get crowded, right? Congested. So what it means is here clearly there is stress concentration, which means smooth flow is interrupted or suddenly diverted, causing a congestion in the flow. Same thing happens with the stress concentration. So stress lines are usually uniform, but if there is sudden obstruction, maybe a hole or maybe an impurity or sudden change in the cross section, that will disrupt the stress lines, and those stress lines would get accumulated or concentrated in that small region that will increase the magnitude of the stress locally. That is what is stress concentration in a nutshell. Now I want you to see what is happening to the shaft because we are cutting the keyway. So this is the shaft, and this is a nice shaft that we designed. And how do we cut a keyway? Using a cutter. And as soon as you cut a keyway, you are creating a sharp edge. And what happens because of this sharp cut? Stress concentration. And because of this stress concentration, what happens? The shaft weakens. So this is called as stress concentration leading to shaft weakening or key weakening. So because of cutting a keyway in a perfectly circular shaft, we are going to make the shaft weak. So how do we take into account the effect of key weakening? The easiest way to do that is oversize the shaft. So if you design the shaft, then increase the shaft size D equal to 1.1 to 1.2 times D design. So after the design of shaft, you're gonna get D design for key weakening. So you find out the value of shaft diameter, multiply that by 1.1 to 1.2 to account for key weakening. Next step, 5, 6, 7. Decide dimensions of the key. If you decide to choose a square key, you can choose D by 4, D by 4, or D by 6, D by 6. Or if you choose to use a rectangular key, it would be D by 4, D by 6. And then you have to find out the length of the key. Find length is equal to F divided by L multiplied by 1/2 H. Tau is equal to F divided by L by W. And I just need to give you so I'll just write this down. This is H, this is W, this is H, this is W. For rectangular key, usually the keys are placed flat. So this is H, this is W. Then find L, select largest L. Everyone understood this? Now the last part is design of sleeve. Now let me remember. In the last class, I gave you an important thumb rule. What was that important thumb rule? It deals with 2 holes. What was the important thumb rule? Yeah.
D inside equal double D outside.
Inside equal double the outside?
Yeah, like
No, outside is equal to double the inside. So this is the D shaft. And this should be 2 times D shaft. Okay. Now think about how this sleeve is going to look like. This sleeve is going to look like this. Do you agree with me? We found out from the dimensions what is the inside diameter and what is the outside diameter. Do you agree with me? One key should fit over here and the second key should fit over here, which means the length of the sleeve should be at least 2 times the length of the key. So this is one length and this is another length. So typically for coupling design or sleeve design, we have to find out if the sleeve is safe in shear. And for that, we have to use the equation of the hollow shaft. So this is D outside. This is D inside. And last but not least is length. Is equal to 2 times length of key plus some clearance. And usually this clearance is somewhere between 5 to 10 millimeter. Are you with me so far?
can I ask you a question?
Yeah.
Can you use just one key or not? the fourth shaft.
Both shaft, one key? No, you need to have two keys. Does it make sense?
Yeah, yeah.
Okay. Okay, now the problem comes is what if the torque requirements are high? Clearly, when the torque requirements are high, a simple sleeve coupling will not work. And what you will have to do is you will have to use something called as the flange coupling, which means what we do is we cut the sleeve into two pieces, add a flange on either side, and attach these two flanges using a bolt. And that is what is called as the flange coupling. We are going to stop here for 15-20 minutes. And then when we come back, so in next part, what I want to do is I want to talk about the flange coupling design. So now what is the difference between a flange coupling and a muff or the sleeve coupling? So in the flange coupling, this is the shaft. So this is the input shaft. Here, there is a flange. Then you have an output shaft. And we have the other side. Something like this. We have keys. And these flanges are attached to one another using bolts. So this is the flange. Key, bolt, and shaft. And I want you to think about this for a second, that if I remove the flange, so if I remove the protruded portion, it's like a simple sleeve coupling. But what is the advantage of this flange coupling? There are two important advantages of this flange coupling. First advantage is it can transmit more power compared to sleeve coupling. Second, what you can have is you can have some type of a rubber bushing here, So you can have a rubber bushing. You can have a rubber bushing. And now it's easy to visualize. So I'm going to show you here bushing. So imagine even if these two flanges, they are slightly misaligned during rotation, that small teeny tiny variation will be compensated by the deformation of the bushing. So imagine that if you have an elastic element, it could be maybe a rubber, it could be some soft material that can be deformed, and it can actually accommodate for teeny tiny variations in that angular displacement or the linear displacement. So the flange coupling, so the major advantages are higher torque capacity, and it can tolerate misalignment. Now, believe it or not, design steps are same as the muff coupling. So I'm going to start with what we have designed earlier. So we will start with the design of shafts. So the first 6 steps are going to remain the same. So design of flange coupling. So step 1, step 2, step 3, step 4, step 5, step 6. Those are the design of shafts. So you will design the shaft. Next step is 7, 8. They are going to remain the same. This is design of key. And now for the coupling, there are some changes. Now let's try to identify what are the differences between the muff coupling and the flange coupling. So if you look at the flange coupling, I'm going to draw slightly exaggerated view. It is something like this. So first and foremost, this is the diameter of the shaft. You agree with me, this will be 2 times diameter of the shaft. And then what we want to do is we want to actually make sure that this design is safe. Typically, this is the pitch circle diameter of the bolts. This would be 4 times diameter of the shaft. And this usually would be 5 to 6 times diameter of the shaft. 5 to 6 D shaft. Now what we need to do is we need to find out the diameter of the bolt. We need to find out the thickness of the collar. I'll call this D. So before I explain the calculations, I want you to pay attention to the dimensions that we already know. The flange coupling has a slightly different design compared to the sleeve coupling. And here, what you have is, you have the diameter of the boss, which is 2 times the diameter of the shaft. You have the bolts and the pitch circle diameter, or the circle where the bolts are drilled or attached, is 4 times the diameter of the shaft. And the outermost dimension is 5 to 6 times the diameter of the shaft. So first and foremost, what we need to do is we need to find out size of bolts. And for that, we need to know how many number of bolts we should use. Minimum, we should use 4. Minimum 4, and you can go all the way to maximum 8 to 12. Depends upon size. But I'm going to assume that we are going to use 4 number of bolts. So what is the force on each bolt? Force on bolt is torque divided by the radius, which is 4 times D shaft divided by 2 divided by number of bolts, N. That gives me the force on each bolt. And what would that force do? That force will try to shear the bolt off. So tau is equal to force on bolt, I'm going to call this FB, divided by pi by 4 DC square. From here, I should be able to find out what is the value of DC. So I should be able to find out the diameter of the bolt. Everyone understood this? So once again, I just want to explain this. We have bolts at the pitch circle diameter. These 2 halves of the coupling are held in place by those bolts. And you have the torque that is acting on the coupling. So in other words, that torque is also acting on the bolt. But if you think about the torque, what is torque? Torque is force multiplied by radius. So I want to find out what is the force on each bolt. So force on each bolt is the torque that is transmitted divided by number of bolts and divided by the radius where those bolts are placed. So that gives me the force on the bolt. And what would that force do? That force would shear the bolt out. So for that, I'm using the resisting area of the circular cross section, equating that to the design shear stress, and that gives me the core diameter of the bolt. Everyone understood this? The next concept is, how do we find out this thickness? Now this is something interesting, and I want you to think about, and this is not new. We have looked at similar failures in quarter joint and knuckle joint. Tell me, if I want to find out this dimension T, what type of failure is possible. Where would this flange fail to find the diameter t, to find the dimension t? How would it fail? Crush it. Tell me, how would it fail? There are different failure modes. So just think.
So the bolt,
So what could happen is the bolt could actually crush this dimension. So basically bolt could crush this dimension. So next part, so 10. So 10 crushing of bolt in flange. So you have sigma c is equal to F divided by, actually this dimension is D multiplied by T. So from here, you can find out the value of T. Are you with me so far? So this will actually give you the design recipe for the flange coupling. And then what you can do is, typically, if you want to add the bushing, the bush would be about typically thickness of 3 to 5 millimeter of some type of soft material. If it's a rubber bushing, it could be anywhere between 5 to 7 millimeter, and you can actually find out the value of the bushing if a bushing needs to be placed to account for misalignment. And that is how you would actually do the coupling design. Okay. Now at this point, I want to ask you, do you want me to solve a problem on the coupling design, start to end? Or you think you can just plug and chug and get the values? No, that's what there is to it, right? I mean, I have given you the recipe. Now what you need to do is step by step, substitute the values, get the answer. And let me look at. Okay. So I'm going to work out this problem. Design a rigid flange coupling to transmit P is equal to 20 kilowatts at 700 RPM. Flanges are made up with cast iron, and other parts made up of mild steel. So sigma T is equal to 60 Newton per millimeter square tau 28 Newton per millimeter square for mild steel and sigma T is equal to sigma C is equal to 110 Newton per millimeter square and tau is equal to 10 Newton per millimeter square for cast iron. So here we have to find out diameter of the shaft, second diameter of the bolt, and third flange dimension. In this problem, we have to find out diameter of the shaft, diameter of the bolt, and we have to find out the dimension of the flange. One thing to observe that this is a rigid flange coupling, which means there is no bushing inside. It's a rigid flange coupling. Power that to be transmitted is 20 kilowatts. And it is transmitted at 700 RPM. Now, flange and shaft, they are made up with different material. Shaft is made up with mild steel. Key is made up with mild steel. And the flanges are made up with cast iron. So CI stands for cast iron and MS stands for mild steel. So which means even though in this problem it is not asked, if you design a key, you will have to use the material properties related to the mild steel. And when you design the flange, you have to use the material properties corresponding to cast iron. Everyone understood this? So we start. Step 1. P is equal to 2 pi nt divided by 60. Power is 20 kilowatts. Q times pi 700 times T divided by 60. From here, we should be able to find out the value of torque. And let me see who has calculator, who can tell me the values. If you want me to solve the problem, you should tell me the answers. And my answer is 272,830 Newton millimeter. 272,830 Newton millimeter.
Yes, you got it right.
Hmm?
You got it right.
Okay. Now, one thing I want you to understand, in this particular problem, we can make this problem slightly complicated by assuming a service factor. But I'm going to assume normal duty. Okay, assume normal duty. So which means I'm not going to multiply by 1.1 or 1.15 or 1.2. I'm just going to assume that this flange coupling is used for regular operation, no overload. Everything is just perfect. So this is the torque that I'm going to use. The next step, I'm going to find out the shaft diameter. Before I go to the design of shaft, I just want you to understand in this particular problem, since it's a design of a coupling problem, that itself is a problem that has about 12-15 steps. So we can't design the shaft using the principal stress theory because we don't have enough information about the weight on the shaft, or we don't know anything about what type of loading is on the shaft, what type of bearing boundary conditions are on the shaft. So when we are trying to design this shaft, we simply assume that the external loads are neglected and we would just use the pure torsion equation. Everyone understood this? If you get a problem wherein they specify the shaft, they specify the bearings or the loads on the shaft, they tell you whether the shaft is simply supported or the shaft is overhang. In that case, that is a hint that you have to use the maximum shear stress and principal stress approach to design the shaft. But in this case, nothing is given to us. So I'm just going to assume that this design is based on just pure torsional loading. Everyone understood this? So equation for torsion, tau is equal to T divided by J multiplied by R. And now the shaft is made up with mild steel. And for mild steel, let me see, FF, FT, oh, mild steel, I made a mistake. This is not 28. This is 40. So please make a correction for mild steel. So this is 40 is equal to 272,830 divided by pi d raised to 4 by 32 multiplied by d by 2. Solve this and you'll get the value d is equal to 32.3 millimeter. Now, one thing that you have to remember in design, we don't make things. We find the dimensions and order them from Amazon, eBay, or McMaster or Granger. Okay, you don't machine. The reason, if you decide to get the shaft machined, it will cost significantly higher than if you decide to buy just a catalog item, items that are readily available in the warehouse. But here, this is the shaft dimension. I'm going to modify the shaft dimension for key weakening. So let's modify. The shaft dimension for key weakening. Which is 1.25 times 32.3, which is about 42 millimeter. And in design, always remember, never ever keep fractions or decimals. So for example, if you get 41.2, round it up. 42. If you get 42.5, round it up to 43. So round on the higher side, because you will never get fractional shafts, fractional couplings. You will always get something called as, there's also a concept which is called preferred numbers. So what you do is whatever dimension you get, round it off onto the higher side. So 42 millimeters. Now next thing is what we can do is, let me see. So if you want, we can design the key, but design of key is not asked. So design key if needed. And I would just go ahead directly to the PCD design, PCD of bolts. PCD of bolts, this is actually 3 to 4 times diameter of the shaft. So I just gave you the 4 times diameter of the shaft, but it could be like 3 to 4 times diameter of the shaft. Hub diameter is 2 times the diameter of the shaft. So I would just say 3 times 42 millimeters, which is 126 millimeters. Dia of hub, 2 times 42, 84 millimeters. And dia of flange, this can be anywhere between 4 to 5 to 6. So I'm just going to assume 4. Now to find diameter of the bolt, I'm going to assume 6 bolts are used as an assumption. So tau bolt is equal to torque divided by the radius, which is 126 divided by 2, divided by 6, pi by 4, DC square. So substitute this 40, T is equal to 272,830. You'll find the value of DC. So quickly tell me, what is the value of DC? Next thing, find thickness. So crushing, Then check hub. And there is one more failure possible that I just want to quickly explain. So tell me the dimensions. What is DC? So 24 millimeters. T. So online students, what is the value of T? So what? How much did you get? 1 millimeter, 2 millimeter? Huh? Oh, 0.1. That is okay. Well, my answer is a different value. So 10 millimeters. But you can check. Find the value of tau here. What is the value here? Is it less than 10 or is it greater than 10? My answer is 3.8, but you can check. So everyone is comfortable in key design, or do you want me to do the key design as well? Comfortable, not comfortable? This is your chance, ask me. Key design okay? Everyone okay? Square key or rectangular key? Okay. So there is one more thing I just want to quickly tell you, and this is slightly different. This is given in the textbook. We have this flange. There is a possibility that this top portion of the flange could stay on the other flange, and this whole thing could crack over here. So what would happen is, please try to visualize this failure. This thing stays in the shaft. This whole thing comes out. So this is a thickness T. So we have to just check for circumferential shear. So tau T divided by 2 times diameter of the shaft divided by 2 divided by pi times diameter of the boss this is 2 times ds. Multiplied by T. Just make sure that is less than 10 Newton per millimeter square for cast iron. Okay, so next part is turnbuckles. So what is a turnbuckle? Turnbuckle is something like you have a composite screw assembly wherein you have the left hand threads on one side and you have the right hand threads on the other side. And then you have screws here. So what would happen? If you rotate the turnbuckle clockwise, these two ends would come together. Because one is a left hand side thread, the other one is the right hand side thread. So if you rotate the turnbuckle, then those two ends would come together. If you rotate the turnbuckle in the opposite direction, those two ends will go apart. Where is turnbuckle used? Turnbuckle is used in lot of applications. For an example, if you go around the power road, you will see that you have these poles, either the electrical poles or the telephone poles, and these poles are reinforced by means of steel ropes. And what you have is these two steel ropes are attached by means of turnbuckle. And this turnbuckle is used to adjust the tension in the rope. So basically, if you rotate it in one direction, that would increase the tension. Turnbuckle type of mechanism is also used in automotive tensioners. So what happens is you have a pulley, so you have an idler pulley. So you have a serpentine belt. That serpentine belt goes around an air conditioning compressor that could rotate the generator, that could rotate the radiator fan and all that stuff. So there is all, this is a serpentine belt. And what you have is you have an idler pulley here. This idler pulley is mounted onto the turnbuckle. What is the purpose of this idler pulley? The purpose of this idler pulley is if you want to replace the belt, you turn the turnbuckle so that this idler pulley goes back, reduces the tension on the bolt, reduces the tension on the belt, you take the belt out. And what you do is you put the new belt, but for the belt to work properly, it needs to have some pre-tension. Why does it need to have a pre-tension? Because please try to understand, this belt is going to rotate at high speed. which means there are going to be centrifugal forces that would naturally try to throw the belt out. So what we need to have is we need to have a pre-tensioner that will make sure that this belt will conform to the motion profile. It will conform to this profile, stay on these pulleys and continue to transmit power from the crankshaft way to the air conditioning compressor, then alternator and the fan belt. Everyone understood this? So this tensioner also will have a turnbuckle. Some new vehicles, rather than a manual turnbuckle type tensioner, it will have a hydraulic tensioner, which means instead of a manual turning turnbuckle, it would just have a sort of a piston, hydraulic piston, and then you need to add the lever arm and actually pull this down and get that belt out. But if you look at the older cars, you would have a manual tensioner where you adjust the turnbuckle and that actually changes the tension or the load on the serpentine belt. Everyone understood this? So, and many a times, I don't know if you have seen those precision compass, wherein what you have is you have a sort of a knob, you rotate the knob, two ends of that compass, they go away. If you rotate the knob in other direction, these two ends of the compass come closer. It is the same thing, you have a turnbuckle. So turnbuckles are very well used in lot of applications. Many a times, what you want to do is you want to attach one rope to other rope to other rope to other rope, but sometimes the ropes can sag depending upon the temperature variation, depending upon the corrosion, or depending upon plastic deformation. So if you have a turnbuckle, you can actually manipulate and compensate for the slack in the rope. Everyone understood this? So you can have a rope attached to a turnbuckle, you have another rope, and say because of the heat, because of the application, because of the rain and maybe some other environmental factors, that rope plastically deforms. At that time, you can rotate the turnbuckle and still adjust the tension. You can take care of that slack. Everyone understood this? So turnbuckles are very important in mechanical design. Now, I want to clarify one thing. In the next lesson, we are going to talk about something called as power screws. What are power screws? Power screws are like lead screws, where you have maybe a screw and you have a nut. You rotate the screw and the nut goes forward or backward. Think about the 3D printer that you have. You have a stepper motor. With the coupling, the stepper motor is attached to the lead screw. That lead screw has a brass nut, and as soon as you rotate the lead screw, whether you are rotating it clockwise or you are rotating it counterclockwise, that nut will go forward or backward. If you have used the lathe or the milling machine or any other any other assembly where the rotary motion needs to be converted into a reciprocating motion, then a lead screw is used. Idea is similar. Think about it, like when I rotate this, I'm converting the rotary motion into the linear motion of the screw. But what is the difference between the turnbuckle and a power screw? Turnbuckle is not designed to transmit power. Turnbuckle can take the load, which means turnbuckle is designed to take forces. Power comes in the picture when you have force multiplied by velocity. In other words, turnbuckle is supposed to be in static condition. You are not going to change, or you are not going to rotate this turnbuckle continuously forward, backward, forward, backward. You will rotate the turnbuckle and let it stay for 3 months, 4 months, 6 months till this needs to be adjusted. On the other hand, if you look at the 3D printer, that power screw is continuously going up and down, forward and backward. So the difference between the turnbuckle design and the power screw design, both of them have nut and bolt. Both of them have nut and bolt, but turnbuckle is used in static application. Power screws are used in dynamic applications. Everyone understood this? So in today's class, I'm going to talk to you about, or I'm going to give you the design recipe for turnbuckle. And in the next class, I will actually talk about the theories of friction and how to design the power screw, screw jack, and scissor jack. So how would you design a turnbuckle? Uh, 3:26. Do you guys need a break, or you guys okay? You guys need a break, or you good? Online students, you need a break, or you guys okay? I can continue. Okay, so I'll give you the recipe for turnbuckle. And there are different variations or the varieties of turnbuckle. So design of turnbuckle. This is the core diameter DC. This is the outside diameter D. This is capital D. This dimension is T. And there are different varieties of turnbuckle possible in design. But I'm just giving you one simple turnbuckle design. This is L. And I just want you to notice that on one side you have clockwise threads, and on the other side you have counterclockwise threads. And there are two types of turnbuckles. First of all, if you look at the turnbuckle, it could have a hex on top. So you can take maybe a ratchet and then kind of rotate it. Sometimes what you have is you have a hole in the turnbuckle, where what you do is you insert a rod and then rotate that rod. So that gives you more torque. So you can have a turnbuckle where you can actually add a ratchet and then basically rotate it, or you can actually insert a pipe and rotate it. So depending upon the torque that is required. So step 1, core diameter, which is DC, and that is found out using direct tension. So if you design the turnbuckle, they will give you the value of P, which is the load in kilonewton. They will give you the value of sigma T, sigma C, tau, and you have to find out the dimensions. Core diameter, which is sigma C or sigma T, is equal to P divided by pi by 4 DC square. From here, you should be able to find out the DC. Step 2.
I get a question.
Yeah, tell me.
So on the book, they put like a design load, which is 1.3, the load we have.
Oh, design load. So again, it depends upon the service factor you use. So many a times,
Because if I did the bulk would be using the design load, not the.
so if I understand correctly, you're saying that they are saying P is equal to 1.3 times P load, right? Design.
Yes.
Is that what they did?
Yeah.
So this is called as service factor, and that depends upon the where the turnbuckle is used. For an example, if I think about it, like if a turnbuckle is used for a power line application, it's clearly not protected. There will be rain, there will be mud, there will be corrosion, there will be some other environmental effects. So you want to slightly over design to compensate for these unknown factors. That is why they use the service factor. So, but I'm just using it in a normal duty operation. That's why I didn't multiply by 1.3. But it's totally okay depending upon what are the operating conditions. Just assume, just say that using the service factor 1.2 or 1.3, and that should be okay. So what would happen if you multiply by 1.3 or 1.2? Your dimensions will be slightly bigger. The process is not going to change. The only thing is dimensions will be slightly bigger. Do you agree? Step 2. Next thing is shaft dia, which is D, DC divided by 0.8. Step 3. Nut dia, which is capital D, which is 1.25 times D. Step 4. Is nut length, which is L, and that comes from the shearing pi times DC multiplied by L. DC is known, P is given, torque is known. So from here, you can find out the value of L. Step 5. Check for crushing, check for threads crushing in nut. So that is pi divided by 4 d outside square minus dc square. So sigma c is p divided by 5 by 4 times d outside square minus dc square. Then you have step 5.
Ask a question.
Yeah,
So on the homework, we don't have the questions first.
you can assume depending upon the material that is given. What is the material given to you? Steel. If so,
I just assume if it's 90 megapascal.
so if steel, sigma c is somewhere between 90 to 100 Newton per millimeter square. Step 5 is coupler plate thickness. Step 6, yeah. And step 7 is coupler plate width. Which is B. So this is the rectangular turnbuckle. So sometimes this is also called as type 1. So there is another turnbuckle which is called as the type 2 turnbuckle. So what is the difference between the type 1 and type 2 turnbuckle? Now what I'm going to do is I'm going to draw a 3D diagram that will give you an understanding of how this turnbuckle looks like. So this is how the type 1 turnbuckle looks. So as you can see, so this shaft can go here, shaft can go here. This is the type 1 turnbuckle. Now, how does a type 2 turnbuckle looks like? In type 2 turnbuckle, So what you have is you have so in type 2 turnbuckle, there is no hole. And what you do is you can use a spanner or you can use a wrench to rotate it and adjust it. But the amount of clearance that you have in between is lesser compared to the type 1 buckle. Everyone understood this? Okay. So I'll just write the steps. Core dia, TC is sigma T pi by 4 DC square. Then nominal dia is equal to D DC D DC 0.8. Nut length is equal to P 1.25 P. Check thread focusing. P nut dia so nut dia is this. And then you can actually did I get the length of the nut? So next class, check threads for shear. And that is how you design type 2 turnbuckle. I don't remember in the homework I asked you to design type 1 or type 2, but either one is fine. Do you guys need a break or can I go on or? Okay, I'll give you quick 5 minutes break and then I will continue. Okay, in the last part of this lesson, we are going to talk about the spring design. There are two types of springs that we use in design, spring design. There is a helical spring something like this. And there is, so this is also called as coil spring. And then there is a leaf spring. So these two types of springs are used in suspensions. For an example, if you see a truck suspension or if you see an 18-wheeler suspension, you will see that usually you would have coil spring that is attached to the chassis. That is, chassis is attached, the spring is on the other side. You have axle and axle assembly. And for small passenger cars, you usually have something called as the coil spring. This is also called as the helical spring.
Is it because the weight or what?
So again, the way is there are advantages and disadvantages for both types of springs. The leaf springs, they can take more load, heavier load. That's why if you see the locomotive springs, they are usually the leaf springs. Truck springs are usually the leaf springs. But coil springs are usually used for a little bit lighter weight. That's why the passenger cars or maybe SUVs, they usually have coil springs. Now, in coil springs, actually there is something called as the air spring also. So I just give you, or they are like bellows. So if you drive Mercedes or Maserati or Lexus, they usually have the air springs, wherein what you have is the air pressure inside is regulated, and that air cushioning provides the compliance or the spring effect. So you have the bellows. Does anyone have Maserati?
I used to say.
Oh, you used to? Okay.
Mercedes.
Oh, Mercedes has air springs. Yeah, but the problem with air springs is in Arizona weather, that rubber cracks and then you have to replace the springs. And that's $4,000 job right there. And it's not basically, yeah, I don't know if you like working on the cars, but I usually don't recommend air spring vehicles in Arizona weather. In California, they work perfect because
A gasoline car with an electrical car to mechanical engineering.
yeah, so bellows. Okay, coil springs are the easiest springs. Leaf springs, they last a long, they take a lot of load. And air springs, they're supposed to be the most comfortable. And the reason for that is, depending upon the air pressure, the ride comfort can be adjusted. I don't know if you have seen in movies, they press the button, the vehicle goes up, press the button, the vehicle goes down. That is because of the air springs that they have. You can change the pressure and change the ride height, ride comfort, and then handling of the car can be varied. So in trucks, what they usually do is the cheapest way to do that is using a composite spring. So what do I mean by composite spring? So what you have is you have this eyelet and the spring is attached over here and the other base of the spring is attached over here. Just so think about it like this. So right now the attachment points for spring is this, and this. Now what you do is if you want to change the stiffness in runtime, how would you change the stiffness of the spring in runtime? You can do that by adding or dropping coils or adding and dropping leaves. So what they do is, and please observe this, on the trucks, there are additional attachment points over here. When the vehicle is not loaded, the attachment points are shown by the arrow. But when the vehicle is loaded, the spring gets deflected. So what you have is you have these additional attachment points. They come in the picture and they change the effective stiffness of the spring. Because what you do then is you drop the coils that you have over here. Everyone understood this?
Yes.
So by adding and dropping coils, you can change the stiffness of the mechanical spring. Something similar can also be achieved in a helical spring. So what we do is, in the helical spring, you basically add a screw. So in helical spring, you have this screw. And if you want to add or drop the coil, you rotate that screw so that what happens is, initially the attachment point is over here. So you have 1, 2, 3, 3 coils in between the attachment points. You rotate the screw, what happens is this goes up, which means you have dropped this coil, which is below the attachment point. The coil below the attachment point is doing nothing. So basically you add or drop coils, and that is the way you can change the stiffness, mechanical stiffness of the spring. In the case of air springs, changing stiffness is just by changing the pressure. But again, there are advantages and disadvantages of each and every design, depending on, yeah.
Can we use the air spring in heavy like buses or not? Heavy vehicle?
Air springs?
Yeah.
Typically, air springs are not used for heavy vehicles.
Because I saw the buses in Denver that those bottom to be the bus.
Yeah, so air spring alone will not be used. Sometimes what they do is they use, and actually that is the design in Mercedes and Maserati. You don't just have bellows, you have bellows coupled with coil springs. So if you look at that whole assembly, that assembly has the bellow and there is a coil spring. So basically that is to make that ride more comfortable. So that way you can adjust, and then you can change the ride quality, you can change the handling depending upon the stiffness of the springs. But you can see there are a lot of variations in spring design, in suspension design, and you will see that in some vehicles on the front wheels you would see coil springs, and on the rear wheel you will see the leaf springs. Okay.
Bellows like dampers?
So bellows, it's air inside. So basically it's like a spring and damper together. Because if you look at an automotive suspension would have a damper. So it's called shock, and then it will have a spring. So this is the absorber or shock, also called as strut. So if you see, it is something like this.
Okay, this,
Yeah, so you, so I don't know if you work on cars, but if you want to change the strut, what you need to do is you will have to take the 3 bolts off of the chassis, and then there are 3 bolts off of the engine hood, and then actually you get the whole assembly out. Otherwise, if you want to take you just want to replace the spring, you take the spring, you use something called as the spring compressor, you compress the spring, you put it inside the damper, and then load the whole assembly. And that job is very dangerous, because once you load the spring, it's a tremendous amount of power, and if something breaks down, it can kill you. That's why basically, if you want to get the suspension job done, it's better you call a professional to get a suspension job on your
just
vehicle.
saw my car start yesterday, it was leaking, so I know how it's like with the spring.
Oh, which is strut leaking?
Yeah, this one is leaking.
How much is minor leak or major leak?
Minor.
Yeah, a minor leak, I wouldn't worry about it. So, but if you want to, so front or back?
No, fronts.
Oh, so hey,
Both
if,
cars, so
yeah, if you want to replace it, then you have to get the alignment done and whole 9 yards. Okay, minimum $800 job. Yeah, depending, it's not Maserati, right?
no, it's yeah, it's a car.
Okay. Maserati is $7,000 job. Okay, so you have the helical spring. This is called as the leaf spring, and this is the bellows. In helical spring, there are 2 types. One is compression spring. The other one is tension spring. So what is the difference between the compression spring and the tension spring? As the word says, compression springs are used for compression application, and tension springs are used in tension application, which means some springs are open like this. These are used for tension application. And some springs are compressed like this. So depending upon the application that you have, you just have open coils or closed coils, and that would change the utilization or application of spring. Now, important thing is spring design. It's based on torsion. So let's look at the basic concept of spring design. So I'm going to show you a spring. There are two important parameters for the spring design. One is the wire diameter, and the second one is the coil diameter. This is called as capital D, which is coil diameter, and this one is called as small d, which is wire diameter. D is called as coil diameter. And the ratio of coil diameter to wire diameter is given as C. Now, if you look at the load P, so the total stress is sigma direct or tau direct plus tau torsion. Tau direct is P divided by pi by 4 d square plus tau torsion is P multiplied by d by 2, which is the torque, divided by pi by 32 times d to the power 4 multiplied by d by 2. So if you look at the total stress on the spring, I want you to look at a teeny tiny area which is over here. So if you look at this teeny tiny area, that circular area, you are going to have the load that is going to create the direct load, direct torsion, direct shear load, and it's going to give you the load or the stress because of the torque. What would be the value of the torque? P multiplied by d by 2 is going to be the torque. P multiplied by d by 2 divided by pi by 32 d to the power 4 multiplied by d by 2. And what you can do is you can simplify this equation, and once you simplify this equation, let me write this equation down. You are gonna get an equation which is something called as 8 PD divided by pi d cube 1 plus d by 2d. So this equation total is going to be 8 PD divided by pi d cube, and as you know, d by d is equal to c. So this equation is 1 plus 1 by 2c. Now, one thing to observe, that spring is not a two-dimensional element. If you think about it, spring is a three-dimensional element. So if you look at this analysis that we have carried out, it only assumes that the spring is in one plane, but spring is actually in 3 dimensions. So to account for this three-dimensional stress or three-dimensional geometry, what we do is we use something called as the Walsh factor. And what is Walsh factor? This factor K. So to account for for 3D geometry of the spring, K in previous equation is modified as four C minus 1, 4C minus 4 plus 0.615 divided by C. This is called as the Walsh factor. Now, the original factor is 1 plus 2 divided by C. This is original. 2D case. And Walsh factor is used in 3D case. And there is one more equation that is used that is given for spring deflection. That is 64 R cube N P divided by GD raised to 4, where R is the coil diameter divided by 2, N is equal to number of coils, P is equal to load, G is equal to the shear modulus, or modulus of rigidity, now there is slight variation in this equation. Please understand, if you have a spring, if you apply the load, the spring deflects. If you plot load versus deflection of the spring, this is P, this is delta. If you plot the load versus deflection of the spring for the linear spring, this load versus deflection is a straight line, and slope of this line is called as stiffness. K is equal to P divided by delta, which is stiffness. So this equation can be modified as, you can take this P, you can take this delta, you can say GD to the power 4 divided by 64 R cube N is equal to P by delta, which is equal to stiffness. So when you design the spring, these are the only two main equations for spring design. All other equations are used for dimensional decision. So for an example, so from the first equation, this equation, tau total will be given to you, value of P would be given to you, the ratio C is the design parameter. This is decided, this is a design parameter. So the only unknown in this equation is small d, which is the diameter of the spring. So value of P is given to you, value of C is given to you. This capital D is C times small d. So the only unknown in this equation is small d. Everyone understood this? The second important equation in here is delta would be given to you. You need to know how much spring would deflect under what load. Load would be given to you, or indirectly they will give you the stiffness. And from this equation, you just have to find out number of coils, N. Once you know the number of coils, once you know the diameter of the coil, once you know the ratio C, then entire spring, the helical spring is designed. Everyone understood this? So in next class, I would work out the problem on spring design, but you are welcome to attempt the homework problem and the quiz problem, because I believe your homework and quiz problem, they are like coupling design and spring design. So you can start working on those problems. If you have any questions, I would be happy to answer. And I will see you on Tuesday. Before I conclude, any questions from online students? How many? Oh, there's only one student. Tristan, any question?
No, I'm good. Thank you.
Okay, any questions from the class?
What did you refer to C as?
Oh, C as the ratio, which is the coil diameter to wire diameter ratio. So, which is actually, the word is called spring index. So C is also called as spring index, which is, oh, spring index. Oh, all these slides will be posted on Canvas. So, and I will upload the video lecture as well. I'm going to stop recording, and thank you very much. Have a good evening and good weekend, and I will see you next Tuesday.